Hi, today we're covering the Chapter 5 review questions from Berean Builders Discovering Design with Physics. So let's just get right into it. We're not going to go over the definition questions as usual because you can get those quite easily from the book. And so let's start with question 2. A hiker walks with a velocity of 1.3 meters per second at 55 degrees for 96 minutes and then changes to a velocity of 1.2 meters per second at 245 degrees for 157 minutes. What is the hiker's final displacement? So I'm going to go back to something that I've done previously and be highlighting things that are vector quantities. So we have velocity, and for this velocity, our direction that goes with that is 55 degrees. We have another velocity, it's 245 degrees. And then our question asks for displacement, and displacement is a vector quantity. So we are going to immediately recognize that at the end, we're going to need a degree value that goes along with the displacement, in addition to the distance that goes with that. So let's go ahead and write out what we are given. Okay, I'm going to call the velocities v1 and v2. Okay, and you could say v01, so you could instead write like v0, 1, something like that. But for me, it's easier to just write v1, v2. We don't have any final velocities that we're doing for this one, and so it's just easy to just use the v1, knowing that it is technically a v0 value. Okay, an initial velocity value. Okay, so my v1 is 1.3 meters per second at 55 degrees. My v2 is 1.2 meters per second at 245 degrees. And then I also have, along with those, 2 times, all right? So my T1, that goes with the V1, is 96 minutes. And my T2 is 157 minutes. Now, first thing I'm going to do is look and see, do my units match up? So I have seconds here, minutes here, and so I know I'm going to need to do a conversion, most likely, and it's just worth it to do it before you get started. So I'm going to go ahead and convert this 96 minutes, multiplying it times 60, and we're going to get 5,800 seconds. And then here, 157 minutes times 60 is going to be 9,420 seconds. Okay, so before I've done anything else, I'm making sure that all of my units are the same. Okay, and this chapter is kind of nice because it's not a lot of new equations and things that we have to learn. We're actually just learning to use what we've already been given in a different way. So with that, we are going to, in order to determine the displacement, we need to get the displacements for each of these individually, and then we can use our equations that we learned in chapter 4 to get what the final displacement is, okay? And the reason we can't do it just directly from this information that we're given is because there's two pieces of information here and they are not the same. So like, for example, if it would 96 minutes on both of them, you would actually be able to use our chapter 4 equations just from the get-go and not have to determine the initial displacements, and then you could determine the final displacement at the end. But we can't do that for this question. So let's determine the displacement for each of these values. And so the equation that we're going to use is way back from several chapters ago, and that is going to be our delta x equals, and I'm going to call this delta x1, okay? Our delta x equals our velocity, and it's technically v naught, right, times time. Now, there's more to this, right? It's technically, you have plus 1/2 the acceleration times the time squared, but there is no acceleration in this problem. The velocity remains constant. And so this acceleration is 0, and so I don't need to use it, okay? So when the acceleration doesn't change, our delta x is simply the velocity times the time. And so for my first velocity, my delta x is going to be 1.3 meters per second times 5,800 seconds, and that will give me 7,500 meters. And remember, it's a vector quantity. It is displacement, and so my direction is still 55 degrees Celsius. Or not Celsius, sorry, 55 degrees, 55 degrees. Okay, now I'm going to do the same thing for my second quantity. So my displacement, delta x2, 1.2 meters per second. My velocity times the time, 9,420 seconds. And with that, I'm going to get the delta x2 equals 11,000 meters. And again, just bringing down this direction, 245 degrees. Okay, so now I have these two quantities that I can use my equations from chapter 4 with to get the final displacement. Okay, so I'm going to get my y values first. I'm sorry, this is delta x1. I'm going to get my y values 1. I'm going to make this value a. So if you're following along with the equations from chapter 4, we call things a, b, and c. So we're going to make this a and this one b. So you have a y. I like to start with y because it keeps me, when I go later, I'm going to be y over x, and so if I do y first, it just naturally goes that way in my head. So a y equals, we have 7,500 meters times sine of 55, and I'm going to get with that 6,100 meters. My by, and I like to do the y's together and the b's together instead of doing a's together and b's together. Sorry, y's together and x's together instead of a's together and b's together. So my by is 11,000 meters times the sine of 245 degrees. And so for my by, I'm going to get, it's going to be 10,000, okay? And that's going to be, so the 10,000, if I write that out, is only one significant figure. And so I'm going to write it out to show that it's still two significant figures as, hold on, yeah, 1.0 times 10 to the fourth. And it's actually a negative 10,000. So negative 1.0 times 10 to the fourth. Now, I think I skipped over this, but there may be more to this, right? But remember, we keep significant figures. So when I did this x2, delta x2, 1.2 meters per second, two significant figures, we're only at 11, okay? And same thing here. We had 1.3 meters per second here, and there were two significant figures here also. So we are at two significant figures with that 7,500, okay? Okay, so now let's do our x values. So AX, 7,500 meters times cosine of 55, and that is going to give us 4,300 meters, and our BX is 11,000 meters times the cosine of 245, and that's going to give us negative 4,600 meters. Okay, so now I can determine my y values and my x values of my c, which is how I'm going to get my final displacement, right? The c is the final displacement. So if you remember from last chapter, right? So what's going on here is this hiker is walking at 55 degrees for 96 minutes. So say it like this. And then he switches to 245 degrees for 157 minutes. So he's kind of doing like this, okay? And so my C that I'm doing is this. This is what my final is going to look like, okay? Okay, so to get the C, I'm just going to add these together. So my CY equals 6,100 meters. This is adding this as a negative, so minus 1.0 times 10 to the fourth. And with that, I get it's going to be, hold on. We're going to get negative 4,000. I'm sorry, this was meters. Meters. Now, why do I not do scientific notation with this one? Okay, well, 6,100, we're doing a subtraction problem. So 6,100 meters, its least significant figure is in the 100s place. And the last significant figure for this one is in the 1,000th place, right? Because this is 10,000, and the first zero is significant, okay? And so when I write this here, this is exactly right. The lowest significant figure is in the 1,000th place, okay? So now I'll do my x values. So CX is 4,300 meters. Minus, and it's minus because this is a negative, otherwise I'd be adding 4,600 meters. Both of these have their least significant digit in the hundreds place. So this is going to be a negative 300 meters. And this falls in line with this diagram that I just drew, right? It's going to be x and y values are both negative. Okay, so now to determine my C value, so what is the actual distance that this C is going, I'm going to use the Pythagorean theorem. And so my C equals my y squared plus, so C squared equals my y squared plus x squared. So negative 4,000 meters squared plus negative 300 meters squared. So now when I square these, I have to keep in mind significant figures, and there's only one significant figure here and one significant figure here. So even though when I square 4,000 meters, I get 16 million, we have to round that to one significant figure. So it's going to be 20 million plus, and then this is 90,000. And then when I add these, also keeping in mind significant figures, my answer has to be to the one with that is the least precise, right? And so this is to the 10 millions place. So this does not affect what, this does not have any effect whatsoever. We're actually just going to be taking the square root of 20,000, okay? So when you add these, just based on significant figures, the answer is 20,000. Okay, so now I will take the square root, and my C equals, and again, I'm going to be taking that to one significant figure, and it's going to be 4,000 meters, okay? So now we have the distance, but we need the angle so that we can figure the displacement. And so we'll use our equation to do that. Now, remember that that equation is, we're taking the tangent of the angle equals cy over cx, right? And for me, the easier way to do this, because we're trying to figure out what the angle is instead, we say angle equals the tangent inverse of cy cx. Because this is what you're actually going to be putting into your calculator. Okay, and so that equals the inverse tangent of, and we're taking our cy and cx from what we have previously calculated. So it's negative 4,000 meters over negative 300 meters. And this is why I always do the y first, so I'm just doing it in the same order as what I did the problem. And with that angle, we're going to get 13 point, and it's 0.33333. Sorry, so this will be 13.33333, repeating, taking the inverse tangent of that, and we get 90 degrees. Now, remember that we are going to the third quadrant, right? We have a negative y and a negative x. We should be in the third quadrant, and so we have to do a little bit of extra math here. I'm going to add 180 degrees. And so the other thing too is if you saw 90 degrees, if you've drawn this out and you've paid attention to this, 90 degrees does not make sense, because 90 degrees would mean this person is going this way, right, straight up. And that's definitely not what happened if you are visualizing it. So 90 plus 180, and they've gone 270 degrees. Okay, and I didn't draw this the best, right? That actually ended up down here, but still, this this tells you what you should be doing. Okay, so my final answer with this, I'm going to put these together, and the final displacement is 4,000 meters at 270 degrees. Okay. All right, and that is question 2. So now question 3. A 915-gram object experiences 2 forces. The first is 15.0 newtons at 299 degrees, and the second is 22.5 newtons at 276 degrees. What is the acceleration of the object? Okay, so let's go ahead and find our vector variables, right? The first is our first force, right? And so this is a force. We can write that in here. The first force, right? And the second force. Okay, and we see that they have those directions with them. What is the acceleration? Acceleration, vector variable, so it's going to require a direction to go with it when we get that answer. So let's write out what we've got. We have a mass, and it's 915 grams. And we have what I call force 1. It's 15.0 newtons at 299 degrees. And force 2 equals 22.5 newtons at 276 degrees. So first I'll use my chapter 4 equations to get my y values of each of these vectors. So my AY equals 15.0 newtons times the sine of 299, and with that, plugging it into my calculator and rounding to 3 significant figures, I get negative 13.1 newtons. For my BY, taking 22.5 newtons times the sine of 276, and with that we get negative 22.4 newtons. For my x values, AX equals 15.0 newtons times the cosine of 299, and I get 7.27 newtons. For my BX, we have 22.5 newtons times the cosine of 276, and we get 2.35 newtons. So now to get the CY and CX values, we'll just add these together. So my CY equals my AY plus my BY, and so negative 13.1 newtons. I'm going to subtract because it's negative 22.4 newtons, and I get with that negative 35.5 newtons. For my x value, I'm going to add 7.27 newtons plus 2.35 newtons, and I get 9.62 newtons. So now I can determine the c value using Pythagorean theorem. So c squared equals negative 35.5 newtons squared plus 9.62 newtons squared, taking the y and the x value and squaring them. And when I do that, keeping it to 3 significant figures for each of these, I'm going to get 1260 square newtons plus 92.5 square newtons. When I add these together, my least precise digit is the tens place. Okay, and so when I round these, I'm going to round to the tens place as far as significant figures, and so I'm going to get 1350 square newtons. Take the square root of both sides, and my C is 36.8 newtons. Okay, so this is my force that I'm going to use to determine the overall acceleration. My overall force is here, acceleration is here, but I still need the direction, and so I'm going to go ahead and do that first before I use that force equals mass times acceleration equation. Okay, so our angle is the reverse tangent, the inverse tangent of my y over my x value. So negative 35.5 newtons divided by 9.62 newtons. And with that, I will get negative 74.8 degrees. So we know this is not the final answer because we can't have a negative degrees here. And so let's look at this and determine what quadrant we're in. Okay, so we have a negative y value and a positive x value. So that means that we're in quadrant 4. And with quadrant 4, we need to add a full 360 degrees. And so my angle comes out to 285.2 degrees. Now, remember, when we are adding these degrees, there is no significant digits that we're worried about because this is an exact number. So we follow the significant digits rule for what we've added to the 360 degrees. So this still goes to the 10th place, 285.2 degrees. Okay, so now we can determine our force, our acceleration using our force equation, right? So remember, force equals mass times acceleration. Our force is 36.8 newtons, and our mass is 0.915 kilograms because we did that conversion up here. And our acceleration is our unknown. So we divide both sides by 0.915 kilograms. And remember that newtons equals kilograms times meters per second squared, right? And so those kilograms are going to cancel. And our final value here is 40.2 meters per second squared equals the acceleration. And so my final answer is that the acceleration of the object is 40.2 meters per second squared at 285 degrees. Okay. And just double checking that, the question asks, what is the acceleration? Acceleration I have highlighted, so I need direction, I have direction, And my answer is answering what the question is asking for. So question 4, what can you say about the x component of a projectile's velocity throughout the course of its travel? What about the y component of the projectile's velocity? Ignore air resistance. I'm not going to write this out. I'm just going to verbally tell you. So the x component of a projectile's velocity is going to remain constant throughout the course of its travel as long as you are ignoring air resistance. So if it starts out at 5 meters per second, it ends at 5 meters per second too. The y component of its velocity may, and usually often does, start as positive, but it will decrease, continue to 0, and then become more and more negative. Sometimes it actually starts at 0, like for example, if something's getting pushed off a cliff, but in general, starts at positive, decreases, continues to 0, and then becomes more and more negative. Now, question 5 says answer question 4 again, but this time include air resistance. Well, if we account for air resistance, the component of a projectile's velocity is going to decrease over time, although it will never become negative. So the x component of a projectile's velocity will decrease over time, but will never become negative. The y component may start out as positive, just like before, but it will decrease, continue to 0, and become more negative, just as before. However, both velocities will be smaller than they would be without air resistance. For question 6, the drawing on the right depicts the two-dimensional paths of 3 different objects flying through the air. Which one is a projectile? And the answer here is that B is the projectile because it has this parabolic path. And projectiles are parabolas. All right, question 7. A projectile is fired with a velocity of 175 meters per second at 55 degrees. If it lands at the same height from which it is released, what are the final x and y components of its velocity? So I'm first, well, let's go ahead and do what we normally do. So we have velocity, and there's the direction, and then what are the final x and y components of its velocity? Now, when we are answering this, well, x is going to be up and down, or sorry, horizontal, right? So it's going to be 0 degrees. Y is going to be measuring it at 90 degrees. So we're actually not going to have a direction associated with this. Once we've broken this down into x and y components, there isn't going to be it's not going to be a vector quantity. Okay, so let's kind of break, I'm going to draw a diagram here. Okay, so this object is being fired from this point, and it's at 55 degrees, so it's like that, right? It's going to be a parabola, and it's going to come back down, and it's landing at the same height as what it was fired from. Okay, so this looks like that, right? And when it leaves, it is 175 meters per second, and this angle here is 55 degrees. So if it's landing at exactly the same height as it's released from. So thinking through what we're given, we have a V naught, and it's 175 meters per second at 55 degrees. So that is this velocity at this angle, but we don't have the x or the y components of what this initial velocity is. But I'm going to fast forward for a second so that we're thinking about what we're going to end up with, okay? So as we said in question 4, the x component of a projectile's velocity is going to remain the same throughout the course of its travel. So once we determine what the x component is, that's going to be our answer. It's the same from the beginning to the end. Now the y component, on the other hand, does change, right? It will decrease until it reaches 0 at this point and continue decreasing, becoming negative. What we know, though, is that because this is at the same height from which it's released, what velocity does, according to gravity, is when it gets to the same height as which it was released, it's the same number except the negative of that number. So when we determine the y component of this initial velocity, we're just going to take the negative of that, and that will be the answer because it is the velocity where it is at the same height from which the projectile was fired. Okay, so to get my x value, v naught x equals 175 meters per second times the cosine of 55, and that is 1.0 times 10 to the second meters per second. So technically we got 100 meters per second, but we need to have two significant figures because of our angle here. And so to show that it's two significant figures and not one, we have 1.0 times 10 to the second. For my y velocity, 175 meters per second times the sine of 55, and with that we get 140 meters per second. Technically it's 143, but two significant figures. Okay, and so my final answer then, as we just discussed, is that the final x component velocity is 1.0 times 10 to the second meters per second because it stays the same. The final y component velocity is negative 140 meters per second because we are measuring that velocity at the same height but the opposite side of the parabola from which it was launched. Okay. So question 8, a sharpshooter is aiming at a target. If the target is stationary, where should he aim to hit the target? If he knows the target will be dropped at the same time he shoots, how should he aim to hit the target? Again, I'm going to just give this one to you verbally rather than you waiting for me to write it out. So if the target is stationary, he should aim above the target to hit it because of the parabolic nature of projectiles. If the target is dropped, however, he should aim directly at the target. And that's because the bullet and the target are going to be accelerating downward at the same rate. And so if he aims directly at the target, he should hit the target. Question 9. A projectile is fired with a velocity of 5.2 meters per second at 33 degrees. If it takes 0.29 seconds to reach its maximum height, how long will it take to reach the height from which it was launched? Okay, so we have velocity, and in our question, how long will it take to reach the height from which it's launched? That is a time variable, and so we actually won't be needing to have a vector quantity and direction in our answer for this one. So let's write out our variables. We have our initial velocity is 5.2 meters per second at 33 degrees. My time is 0.29 0.29 second to max height. Okay. And so I'm going to draw another diagram. So we're launching here and ending up here. Okay, the height is the same from launch to landing. And this time period is 0.29 seconds. Okay. Well, what we know about these parabolic functions is that if we are beginning and ending at the same height, the times on each side are the same, right? So this is another 0.29 seconds. And so actually all we are doing here, this velocity is not relevant to the problem. All we are doing here is doubling the time. So 0.29 seconds times 2 equals 0.58 seconds. So it will take 0.58 seconds from the time of firing to reach the height from which it was launched. For question 10, it asks us, what is the maximum height of the projectile discussed in the previous problem? What are the values of the x and y components of its velocity at that height? So for this one, we need the information from the previous problem. And put this up here. And if you remember from the previous problem, this velocity was given to us, and I was like, well, we don't need this. This was just excess information. Well, turns out we're going to use it in question 10. So it wasn't the text just trying to be tricky with us. We were actually going to end up using it eventually. So we're going to need the velocity because we're going to be taking the x and y components of the velocity. And remember that x and y components will not be vector quantities. So we will not end up needing to use any directions, any degree values for our ultimate answer. Okay, but we do have two parts of this, maximum height and the x and y components of the velocity. So what we need here is that initial velocity from the previous problem, which was 5.2 meters per second at 33 degrees. And the time. That time is 0.29 seconds. And remember, that is the time that it takes to reach that maximum height. So we're being asked now, what is this maximum height? And then when we're at this height, what are the x and y components of the velocity? So let's go ahead and start with figuring out what the maximum height is. And a good place to start when we are given a velocity and a degrees is let's go ahead and separate that out into the x and y components. Okay, so the v naught y, so I'd just like to do y first, is going to be 5.2 meters per second times the sine of 33. And with that, we'll get 2.8 meters per second. So when that projectile is fired, it starts out as 2.8 meters per second in the y component. The x component use cosine, and we're going to get 4.4 meters per second. So now that we've done this, we can actually already answer the second part of this question. So what are the values of the x components and y components of its velocity? So we know that x component does not change throughout the course of a projectile's travel. The velocity does not change. And so the x component is going to be 4.4 meters per second. We also know the y component, and we didn't need to use either of these to figure this out. And that's because we are at the top of this parabola at the maximum height. And so at this height, this is where the velocity is transitioning from positive to negative. And so the y component at this maximum height is going to be 0. It starts out at 2.8 meters per second, but it is going to be 0 when it's at the maximum height. So we'll just keep that in mind and write it in with the final answer. But let's go ahead and continue with determining what the maximum height is. Now there are at least two possible ways to do this problem, and very likely there might be some other problems in this chapter that you've done a different way. And as Dr. Wile says in the book, if you got the same answer, then you're doing fine. You just found a different way to do it, and that's fine. There are multiple ways to do a lot of these problems. I came across this one because I did it a different way than what the solutions manual showed, and so I'm going to show you both ways just to demonstrate that there are a couple of ways to get the answer to this problem. So the way that I determined this is using this delta x equation. Okay, using my displacement equation. So my delta x, my displacement with the y variable, equals, we have velocity times time plus 1/2 acceleration times time squared, because we have everything here except that delta x. So our velocity here, our initial velocity here is 2.8 meters per second times 0.29 seconds plus 1/2. Our acceleration is going to be negative 9.81 meters per second squared, and then times the time squared. Okay, and so when I calculate all that out, I'm going to get 0.81 meters per second squared, or sorry, not meters per second squared, just meters. That's because seconds is going to cancel out right here. So 0.81 meters plus, this is actually negative because of the negative gravity value. So, or the negative acceleration. Okay, so minus, we'll say 0.41 meters. Okay, and so my delta x for the y component equals 0.40 meters, and that is the height at the maximum height value of the flight of the projectile. Okay, and so, and how we knew that is, we know 0.29 seconds, and that's how long it takes. And so with using that acceleration, the initial velocity at 2.9 seconds, that's the highest, and that is 0.40 meters displacement from the original launch site. Now let me show you how to do this the other way, a second possible way. So the second possible way would be to use this equation using final velocity and initial velocity and acceleration, and then we have our delta x at the end. Okay, and so our final velocity is 0 because we are at the top of that parabola with a 0 velocity. And our initial velocity is 2.8 meters per second. I'm squaring all that, plus 2 times negative 9.81 meters per second squared, and then times our unknown delta x. Okay, and so we then get negative 7.8 meters squared second squared. So 2.8 meters per second squared is 7.8. Moved it over to this side, equals, and the 2 times negative 9.81 is negative 19.6 meters per second squared times delta x. Divide both sides by that negative 19.6. I'm going to end up everything canceled except a meters. And then our final value is 0.40 meters equals delta x. So 2 ways to get exactly the same answer for that problem, and I just wanted to demonstrate both of those for you. So especially if you chose one and I'm doing it totally different, you can see that what you were doing was just fine. So now we can write in our final answer. The maximum height is 0.40 meters. The x component velocity is 4.4 meters per second. The y component velocity is 0 meters per second. And that's our answer for this one. So we just double check that we've answered everything. Maximum height, we have a meters value. X and y components of velocity, we have x, y, and velocity is meters per second. So we are good. For question 11, we're asked to determine what is the range of the projectile discussed in problem 9. So up to this point, we've basically used only equations that we've learned in previous chapters and just applied them in different ways to determine the answers for these problems. And so this is the first problem where we have a new equation that was just introduced in this chapter, and that is the range equation, which is equation 5.10, and it says range equals, we have the velocity squared times sine of 2 times the angle divided by gravity. Okay, this is not a vector equation. It is always positive, and so we don't need to do any highlighting here to remind ourselves of vector quantities. So for this then, our velocity was 5.2 meters per second. So 5.2 meters per second, and we are squaring all of this times the sine of 2 times our angle, which is 33 degrees, and then dividing all of this by our gravity, which is 9.81 meters per second squared. Okay, and so once we throw all of this in a calculator all at once, we get, with 2 significant figures, 2.5 meters. And range should be a distance value, and that's what we have. So the range is 2.5 meters. Pretty simple. For question 12, one player throws a baseball to another player. If the angle at which the ball was released is 39 degrees and the other player catches it 45 feet away at the same height, what was the speed of the pitch? Okay, so our angle is 39 degrees and our range is 45 feet. And this at the same height part of the question is a key thing here, because that is part of the definition of the range. The heights have to be the same between point A and B when it was released and the end point at which you're measuring, okay? And so we can just plug these into the range equation. And I'm not going to rewrite the equation that is up here. We're just gonna plug it in. So range 45 feet equals, we have velocity squared, which is our unknown, times the sine of 2 times 39. We're dividing all of that by, remember that we're dealing in feet here, so we're going to use 32.2 feet per second squared. Okay, and so then I am going to multiply both sides by 32.2 feet per second squared over the sine of 2 times 39, which is 78. Okay, and I'm going to kind of do all of this at once. So multiply both sides by that, and then take the square root. Okay, so what's happening is I'm getting rid of this, right? I'm left with velocity squared equals this, and then taking the square root of both. And so once I do that, it's going to be 38 with 2 significant figures, because I have 2 significant figures here, feet per second equals the velocity. So the speed is 38 feet per second. For question 13, a gun on a ship fires its shells at a speed of 775 meters per second. If it is trying to hit another ship that is the same height and 8.55 kilometers away, at what angle should the gun be fired? So this is going to be another range equation because it's telling us it's the same height. Here's the distance or the range, and here's the velocity. And this time we're missing the angle portion of the range equation, okay? So our velocity is 775 meters per second, and our range equals 8.55 kilometers, okay? And I pretty much always like to, first thing I'm noticing is that I have meters and kilometers. And so I'm going to go ahead and convert this to meters. So that's going to be 8,550 kilometers. Okay. So now I'm just going to plug all this into my range equation. So range, 8.55. Oh, and I just switched that to meters, and then I started to write down the kilometers. 8,550 meters equals my velocity squared, so 775 meters per second squared, times the sine of 2 times my angle, which is our unknown, times gravity, or divided by gravity. So 9.81 meters per second squared. Okay. And so we will multiply both sides by 9.81 meters per second squared divided by 775 meters per second, and all of that squared. Okay, so we're going to have all this canceled out except for the sine of 2 times the angle. And so I'm going to get here 0.1396. And in this case, it might be a good idea to, whatever you get here, just leave it in whatever number of figures it is, whether all of them are significant or not, because then we're going to use our sine equation. But there's quite a few number of digits here, and so it should be enough for us to get a pretty accurate answer. But so that's going to equal sine times 2 times the angle. All right, and so what we're going to do with this then is we're going to take the inverse sine of this, and so if we do that here, sine -1 of all this, you're going to end up with 2 times the angle on this side, and 8.03 here. So now we'll divide both sides by 2, and we get 4.02 degrees equals our angle. Okay, and so that is our answer. The gun should be fired at 4.02 degrees. For question 14, I'm just going to verbally tell you this because it's not a calculation question. So if you want to maximize the range of a projectile, at what angle should it be released? And that answer, as given to us in the book, is 45 degrees, and that's because that is what makes the sine of 2 times the angle the largest. So 45 degrees will always equal our maximum range of a projectile. Question 15. An archer's bow can shoot an arrow so that its range is 51.0 meters. If the archer uses a bow that shoots the same arrows with 3 times as much speed and shoots at the same angle, what will the new range be? So we have a range of 51 meters, and we know that a 3 times higher velocity is going to be the new range, or we're going to use that to calculate a new range. So we're not given a lot of information here, and we really don't need a lot of information, because what we're really just saying we're given 3 times this much speed, and what will the new range be? And so let's look at our range equation. Range equals, we have v squared times sine of the angle. And so we're not given this angle, right? Or the initial velocity divided by gravity. But if the new range, or the new velocity, is 3 times higher, what's going to happen to the range is that we have a 3 here that's going to be squared. And so ultimately, the range is going to be 9 times higher. Okay, that's the only thing that is changing within the equation to get the new range. And so, to get the new range, we're going to say 51.0 meters times 9, and that is going to equal 459 meters. So the new range will be 459 meters. Question 16. A man throws a ball with a velocity of 39.1 feet per second at 42.5 degrees. It lands on the ground 51.0 feet from where it was thrown. And how far off the ground was the ball released? And it gives us a nice drawing to be able to visualize this. So we don't have to draw a drawing this time like I like to do. Okay. So again, we're not going to use any vector quantities because our how far off the ground, that's just going to be already, it's going to be this high off the ground. It's not going to be below the ground, right? But we do have velocity with that angle to start with. Okay, so let's write out what variables we're given. We have initial velocity, and it's 39.1 feet per second at 42.5 degrees. We have a delta x, our displacement is 51.0 feet from where it was thrown. Okay, and so as Dr. Wile says in the book, we are generally going to start with the opposite component of what the question is asking for in order to get ultimately to what the question is asking for. So how far off the ground? This is a y component question. And so a good way to start is to think, okay, I'm going to need to figure out my x components first. But let's go ahead and figure out both together what the y and x components are of this initial velocity. Okay, so my y component of my initial velocity is going to be 39.1 feet per second times sine of 42.5, and I'm going to get 26.4 feet per second. My x component, 39.1 feet per second times cosine of 42.5, and for that I'm going to get 28.8 feet per second. Okay, so I'm going to start here, and what I really need to figure out is time from here. I have velocity, I have the total displacement from an x standpoint, and I don't have time. So let's use this equation of delta x and equals velocity times time. And remember that there's technically a plus 1/2 acceleration times time squared here, but acceleration is 0, and so we're just not going to even include that. So my delta x, my displacement, and it's from an x standpoint, is 51.0 feet. My velocity for x that I just figured out is 28.8 feet per second, and then I have time. Divide both sides by 28.8 feet per second, and I'm going to get 1.77 seconds as my time value. So now that I have time, I can insert it into an equation for my y value to determine what the displacement is for y. Okay, so this is y. So my delta, I'm going to use the same equation. Delta x equals my initial velocity times time, but this time I'm going to include the 1/2 times the acceleration times time squared because I do have an acceleration in my y value, and that is gravity. So delta x equals my y velocity is 26.4 feet per second. My time that I just figured out is 1.77 seconds. Acceleration, 9.8, sorry, not 9.81. Remember, we are dealing with feet here, so I can't use the meters. Gravity, so 32.2 feet per second squared, and then time squared, so 1.77 seconds, and that's squared. So calculating out each component of this addition problem, I'm going to get 46.7 feet, okay, because my seconds are going to cancel, plus, and this is actually going to be negative, and I didn't include the negative here, but this 32.2 feet per second is negative, okay, and so instead of a plus, it's going to be minus 50.4 feet. Okay, and again, that's because the seconds cancel. We're left with feet. And if you don't have the same units here, you've done something wrong. So nicely, these have the same least significant digits. So the answer is 3.7 feet negative. So that is my displacement. Now, this means that the landing spot, the displacement from when the ball was thrown, is 3.7 feet below where it was thrown, okay? And that's not what the question is asking. The question is asking how far off the ground was the ball released, not how far down it went. And so we're going to switch this sign in our actual answer. The ball was released 3.7 feet off the ground. Okay. Question 17. A boulder rolls off a cliff with a velocity of 16 meters per second at 0 degrees. If the cliff is 15.0 meters above the surface on which the boulder lands, how far from the edge of the cliff will it first hit the new surface? Okay, so we have a velocity and the direction is 0 degrees. And we're going to be determining how far from the edge of the cliff it will first hit the new surface, okay? So our final variable is going to be using our x component of velocity to get to it, okay? what we're asking for. So let's put what we're given together. We have velocity equals 16 meters per second at 0 degrees. We have our delta x y value is 15, and it's actually negative 15.0 meters, all right? Because when it comes down here, it's going to drop 15 meters. So this is negative. So we actually don't need to do a lot of equations to figure out what our velocity, y component velocity is, or our x component velocity, because this is at 0 degrees. So our y component velocity is 0. That is what we're starting out as. Okay? Because it is just going straight off this cliff. There's no up or down motion to this boulder initially. Okay? And this is our initial velocity. Our x component velocity is going to be this, right? Because we're at 0 degrees, this is horizontal velocity, and so our x component velocity is exactly what we were already given. Okay, so that's easy. We don't have to figure out either of those. So now we can use what we have to determine this. Now, once again, we are needing an x component, so we're probably going to have to use something from the y component first to get some information that we can determine x. Okay, and so indeed, let's figure out the time, right? We know what the velocity of x is, so what's the time that it takes to get to whatever meters this is going to be. And so then we're going to determine what the time is for it to travel 15 meters with the y component. Okay, so our delta x, and we're determining it for the y component, equals let's go ahead and just put the whole equation here. So velocity times time plus 1/2 acceleration times time squared. Okay, remember we are always including acceleration when we're dealing with the y component because of gravity. So our delta x y is our given one here, negative 15.0 meters. Our velocity initially is 0 meters per second. And we can go ahead and put a time here, but we're going to ultimately not use that, right? Plus 1/2 times a negative 9.81 meters per second squared, and time squared. Okay, and so then when we divide both sides by this, I'm not going to write this out this time, but we'll get 3.06 seconds squared equals time squared, and then we can get the square root. And so we end up with 1.75 seconds equals our time. So now that we have the time, we can use it to determine what the delta x for the x component is. So our delta x equals velocity times time, and so that equals 16 meters per second times 1.75 seconds, and that ends up as 28 meters when we put that into two significant figures. And so our final answer is that the boulder will hit 28 meters from the cliff edge. Just double checking that that's what it's asking for. How far from the edge of the cliff will it first hit the new surface? And that is what we are answering. Last question, number 18. A sniper rifle shoots its bullet horizontally, so our angle equals 0 degrees, hitting a target 1.1 kilometers away. If it ends up 7.22 meters below the height at which it was fired, what is the speed at which the rifle shoots its bullets? Okay, so we have a direction value here. We're not going to use it too much because it's horizontal, and our final question for this is what is speed. So we're not actually asking about velocity either for this, so no direction is required. Okay, so let's write down what we have. Our angle equals 0 degrees. Our delta x is 1.1 kilometers. And I remember that I'm seeing in meters here, so I'm going to go ahead and convert this to 1,100 meters. And then our delta x for the y component is 7.22 meters below the height at which it was fired, so it's a negative 7.22 meters. So here we're going to determine, we don't know the speed and we don't know the time, so we can't really do anything with the horizontal yet. But with the vertical, with the y component, we have our initial velocity, which is going to be 0, because for the same reason that the last one was 0. This is angle is 0 degrees, so our y velocity is 0. But our acceleration, we know, and so then we can use that to determine time. So we'll use this equation, delta x, y equals, and so we have that velocity times time, but that's going to be not used in this one because that velocity is 0, plus 1/2 acceleration times time squared, right? So we know our delta xy, negative 7.22 meters, equals 1/2 our acceleration, negative 9.81 meters per second squared, times time squared. So we're going to divide both sides by this. I'm not going to write that out, but that's what we're doing. So negative 7.22 divided by all of this to isolate the t squared is 1.47 seconds squared. And now we will take the square root and we get 1.21 seconds equals our time. Okay. And so now we can plug this into our x component velocity equation. So our delta x equals velocity times time. Our delta x is 1,100 meters equals our velocity, which is our unknown, times our time, 1.21 seconds. And divide both sides by 1.21 seconds. And with that, we'll get 909 meters equals our velocity. Okay, now we need this to be in two significant figures because of this 1,100 meters, so 910 meters is what we will actually report. Now, In this particular instance, we actually would have been okay not converting the kilometers to meters, because in this equation, all that we brought over from here was time. And so we technically could have still kept this as 1.1 kilometers, and our answer would have been, and I didn't have my units here, our answer instead would have just been 0.91 kilometers. I am not putting my right units at all. Kilometers per second. Okay. So either of these answers is correct, 910 meters per second or 0.91 kilometers per second. So finally writing this out, the bullet's speed is 910 meters per second or kilometers per second, whichever way you did it is fine. And that's our answer for 18. So as always, if you have any questions, comments, go ahead and leave them at the bottom and I'll do my best to answer them.